In today's video, we're going to be looking at what similar triangles are and how we prove that two similar triangles exist. Okay, so two triangles are said to be similar if they both have the same shape, but they're a different size. So it's pretty much one triangle is double or triple or quadruple the other, but the shape is very similar. Okay, this means when it's a similar shape, it means that the corresponding angles are equal. Okay, so angles have to match, all the angles have to be equal to each other, and the ratios of corresponding sides are equal, which pretty much means if I take one triangle and multiply all the sides by the same value, I'll get the other sides of that second triangle. Okay, so let's look at number one, just to show what it means to be similar. So we're going to start with the angles. Okay, it tells us that triangle ABC is similar to triangle DEF. List all the pairs of corresponding angles. If we look at our diagram and we know our angle notation, we can see that angle A and angle D are equal to each other. So angle A is equal to angle D, okay, because they each have that one curved line. If I look at my two tick marks, that would be B and D. And then the last angle is equal, the C and the F. Now what you should notice is that your similarity statement, the fact that triangle ABC is similar to triangle DF, all the angles are already matching. Angle A here goes with angle D, just like in our angle equality. Angle B goes with angle E, and then the C goes with the F. Okay? Now, let's list all the pairs of corresponding sides. Now we have to list them as ratios. So if I look over here, from A to B, it looks like it's matching D to E. So I'd write that as AB over DE. In other words, if I divide those two side lengths, it's going to have to equal the ratio of another pair of side lengths that are matching. So if I look over here, the BC should match with the EF. Okay, and notice I'm putting the side lengths of the same triangles on top. So all the small triangles are going to go on the top, and all the big triangle side lengths are going to go on the bottom. And then AC goes with DF. Okay. And that's it. Okay. All the angles are equal, and then the corresponding sides, if I were to create ratios out of them, all the ratios would be equal to each other. Let's look at another one. Triangle BAC is similar to DEC. List all the pairs of corresponding angles. So I'm going to use this actual statement to find my matching angles. So the first letter here has to match with the first letter in my second triangle. So B and D should match. Angle B equals angle D. But we can actually use our Z pattern, or the alternate angles, to see that as well. I have a Z pattern right here, and angle D and B are equal to each other. Okay, I'm going to go back to my similarity statement. The second letter, A, should match with the second letter in the second triangle, E. So angle A and E should match. Let's see if that's true using our rules. Well, I have another Z pattern, or alternate angles here, and E and A actually do match, which leaves angle C with angle C. Okay. And that would be because we have opposite angles. Now that we have that, let's list our pairs of corresponding sides. Now when you have these kind of rotated triangles, you might not be able to notice which sides correspond with what. So in this case, the statement might actually help you. I'm going to write it out to the side so that it's a little bigger. Okay, this is how we would state that our triangles are similar. Okay, now I'm going to take my side lengths straight from this statement, and then I'm going to compare it to my diagram. I'm going to look at the first two letters, BA. So side BA is going to match to the first two letters of the second triangle, DE. So I'm going to write that as BA over DE. If you wanted to write AB, it does not make a difference. So let me look over here. BA is my base right here, and that's going to match DE right over there. So those two sides correspond. Now I'm going to look at my second and third letters. AC is going to match EC. Just looking at the diagram, EC is right here, AC is right here. So those two sides would correspond. So that was AC over EC. And last but not least, I'm going to look at my outer letters. So that's BC going with DC. So BC is right here, DC is right here. So I'm going to write that out. Now we don't have any side lengths, so it's not like we're actually proving anything, but we're just trying to find the connection between the similarity statement and the triangle. And also just looking at the triangle to see which angles would be equal, which sides would correspond. Okay, let's try one more example. And in this case, our triangles are actually nested. So I have a small triangle within a big one. So I have triangle BDE, which is this one right here, the little one, is similar to BAC. So again, I'm going to use my statement and my actual diagram to prove what angles and what sides correspond. So looking at my statement, I would predict that B matches angle B. And that makes sense because, well, it's a shared angle. Both triangles contain that one. Okay. I go back and I look at my second letter, D and A. Angle D equals angle A. And if I'm looking, I actually have an F pattern because I have parallel lines. Here's a backwards F, and angle A and angle D are equal to each other. And the last one would be E and C, and that's also an F pattern with my parallel lines. And those two angles would be equal to each other. Okay, and now let's look at our corresponding sides. Again, I'm going to write out my statement a little larger. Here it's a little easier to see which sides would correspond. Like I would assume that the bases of my triangles match, so DE and AC, but let's actually check that out. So DE is second and third letter, and it should match AC, second and third letter, and it does. So this side matches this side. DE over AC. Okay, and then let's look at another pair. I'm going to put this one in blue. BD should match BA. BD is right here, and BA is that long length in the larger triangle. Okay, and last but not least, we have BE, which is this side right here, should correspond to BC, which is right over here. BE over BC. Now, knowing how to identify which angles are similar and which sides are corresponding is going to help us prove that triangles are similar because they have to follow this outline. Okay, so let's try to actually prove similarity and write our similarity statement. Now, yesterday we looked at congruent triangles and they had a few sufficiency conditions, and same thing with similar triangles. There are three different ones. The first one is angle-angle similarity. So the minute that you know that two angles in your triangles are congruent, so they're equal, your triangles are automatically similar. Okay. The next one is side-side-side, or SSS, and if you know that the three ratios, so you have all three sides of both of your triangles, if you notice that the corresponding ratios are equal to each other, then you have a similar triangle. And the last one is side-angle-side. Now, you have two sides, and you know their ratios are equal to each other, like the corresponding ratios, and then the contained angle is equal to the other contained angle. So that would be side, angle, side. So we're going to practice proving with all three conditions. Okay, so the first one, I'm not given any angles, so the only sufficiency that I can use to prove this would be side, side, side. So in this case, you kind of have to make a little guess what sides you think are matching. But just looking at it, the 5 and the 10, the 2 and the 4, and the 6 and the 12 look like they're matching just because the shapes already look like they're rotated to match. So to prove that they are similar, you have to actually show that the ratios are equal to each other. So the way I'm going to do that is, it doesn't matter if you put small triangle or big triangle on top, but I'm just going to go in order. 5 over 10 is equal to 2 over 4, and it's equal to 6 over 12, all equal a half. So all of the ratios of our three sides are equal. Okay, that's your side, side, side proof. And now let's actually write our sufficiency, or our similarity statement, sorry. And make sure you write the similarity statement with the corresponding sides and corresponding angles. So our angles are, or our triangles are already rotated properly, so I can go ABC is going to be similar to DEF, because I can kind of tell which angles are going to be equal to each other. Let's try another one. I don't have all three sides, so I know I'm not going to use side, 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 but I have two sides and the contained angle of each. So right now, just using the angle notation, I can tell that angle B is equal to angle H. I don't have any other angles, so I have to rely on my ratios. So it looks like these angles aren't perfectly lined up, but the 3, I think, matches the 6, and the 4 would match the 8. So now I'm going to write my ratios. 3 over 6 equals 4 over 8. They both equal 1/2. Okay, so this would be your side, angle, side proof. Okay, now when I write my similarity triangle statement, I'm going to start with B, I'm going to start with H, because I know those are equal. And then from there, I kind of have to visualize this being rotated so that my triangles do match. But pretty much if the 3 centimeters goes from B to N, it matches with the 6 centimeter side, so that would have to go from H to D. So that would be my next vertex. And then the third one, K, goes with R, because we haven't used that. So make sure everything's matching, your sides match as well in your statement. Okay, in this next example, I don't have any sides, so this is probably going to be the angle sufficiency. And I'm going to have to rely on my angle properties. So I see I have two parallel sides, which means I have my Z rule or my F rule. And in this case, I have my alternate angles rule. And it tells me, in this first scenario, that angle A is equal to angle P. I can create another Z pattern right over here, the other way around, and that one's telling me that angle X is equal to angle D. And then the minute two angles are equal, the third one automatically has to match, because all three angles in a triangle have to add up to 180 degrees. So if you want to write angle F equals angle F, you can, but it's not really mandatory. I like to write it just so I can write my similarity statement in the next line. But this proof was angle, angle. Okay, so my statement is going to be triangle AXF is similar to triangle PDF. I think the angle proofs are the best ones, because it's the easiest to write your similarity statements from, just because you already see what angles are matching using your angle properties. Let's try one more when our triangles are nested. So I have a little triangle in here, and then I have a big one in here. And I see I have two parallel sides, so again, I'm probably going to be using a Z or an F rule. And in this case, I can create an F right here so that B and C are equal to each other. So angle C equals angle B. And then I can create another one backwards so that angle D and angle E are equal to each other. And when I write my angles that are equal to each other, I make sure I start with the same triangle each time. So in this case, I started with the vertices from the bigger triangle. And then if you want to write that angle A is equal to angle A, you can, just for your statement later on. And again, this was an angle, angle proof. So my similarity statement, I really just go in order of this. CDA is similar to BEA. Okay, so I want you to try this next one on your own. Notice you're not given any angles, just sides, which means you are going to be using that side, side, side proof. So pause the video and try it on your own. Alright, so I highlighted which sides I thought were matching. So the 10 and the 15, the 8 and the 12, and the 12 and the 18. So I wrote out that those fractions were equal to each other, and when I simplified each fraction was actually equal to 2/3. You don't have to simplify it as a fraction. If you want, you can check each ratio to see what the decimal is, and if the decimals match, that's perfectly fine. Okay, so this was the side, side, side proof. And your statement should be CBF is similar to ADE. Of course, you might have chosen a different order for your letters, so maybe you did BFC, that would have to match DEA. Just make sure you're going in order. So I started here, and then I went in this rotation, so I did the same thing with my second triangle. Alright, I want you to try example F on your own, so pause the video, and then come back to check your work. Alright, so you should have noticed that angle A matched angle X, okay? Angle C matched angle Z, which means B has to match angle Y. So after I wrote that out, it was the angle proof, and I just followed the order of my letters. A, C, B, X, Z, Y. Alright, go ahead and try example G. Try to think of what proof would satisfy this, because we do have two sides. So try it out, and then check back once you finish. Alright, so in this case, because we were given two sides, it was probably going to be side, angle, side, just because we weren't given the third one. Okay, if you're not sure which ones match, you might have to try a few variations, but I thought the 20 and the 30 would match, and the 16 and the 24. And I just showed you a different way you can show that. So I wrote out my ratios separately, 20 over 30 and 16 over 24, and I simplified each one. That way I can maybe more clearly see that the ratios are equal. So either method is fine, this one or the original one I showed you. And then I also put the contained angle, so angle R equals angle R, and that was because they were opposite angles. So I used side, angle, side, and my similarity statement would be QRP is similar to TRS. Now I put QR and TR as the matching ones because, well, those are my blue matching sides. Okay, I want you to try H on your own. Okay, try to separate these into the two similar triangles. Maybe you want to redraw them if this is hard to visualize, and then you can try to prove the similarity. Now notice you are given two sides, so this might be a side angle side proof, okay, just because you're not given that third one, so that should help guide you. Alright, so I'm just going to walk through my thinking process here. So I drew out my two triangles, which was this big main one, and then this little one over here. Yes, we have a triangle here as well, but that one doesn't have any labeled sides, so that's probably not going to be part of our similar triangle setup. So I put EDG and FDG, and I labeled the sides accordingly. Now, what we should notice is that both triangles share this angle G. So automatically, I know angle G equals angle G, and that's going to be my contained angle. Now I look at my sides. Now, you might not know which ones match because, well, it's hard to visualize, but the 8s aren't going to match because I can't have the same side for the triangles to be similar, or else it would be congruent. So this 8 is probably going to match with the 6.4, and then the 10 is going to match with the 8. So I'm going to write out my two ratios. I'm going to use that other method. So 8 over 6.4 and 10 over 8. And I'm actually just going to use my calculator to simplify these ratios. So when I do 8 divided by 6.4, I get 1.25. And I hope when I do 10 divided by 8, I get 1.25. And I do. So this is a side angle side proof. Okay, and now I can write my statement. I know I'm going to start G for each one, just because I know it's the shared angle. Now I'm going to look at my red side. GD is in the first triangle, while GF is in the second. So I'm going to write that at the beginning. And then I have one angle left, So E from the first and D from the second. So now I guaranteed that everything is correct because I know I matched one of my corresponding sides. And that's it for proving similarity. So you have angle, 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 which I find the easiest. You can prove with all three sides, so set up your three ratios and make sure that they're all equal to the same number, or side, angle, side. So two ratios match and then the contained angles are equal to each other. And understanding how to prove similarity is going to be important for tomorrow when we actually start solving similar triangles.